Hello everybody! So today we are going to be continuing our unit on solutions. The next conversation that we're going to be having about solutions revolves around the solvation process, so how things get dissolved. You guys already have a couple notes on this. You guys watched a video on it last Thursday. You saw how water molecules dissolve sodium chloride. Today, tomorrow, and Thursday, we are going to be getting into the nitty-gritty for how we know certain types of solvents can dissolve only certain types of solutes. Okay? But before we do that, we're going to talk about VSEPR theory, which should be a review. We learned about VSEPR theory way back at the beginning of second semester, because in order to understand why certain types of solvents dissolve certain types of solutes, you need to make sure you understand molecular shape and polarity. So that's what we're going to review today. You guys should have picked up on your way in a blue packet that was titled Molecular Shape Affects Polarity, or VSEPR theory. To start, let's review with what VSEPR theory means. So VSEPR theory is an acronym that means valence shell electron pair repulsion theory. That's what VSEPR stands for. So at the top of your packet, you guys should see that. Valence shell electron pair repulsion theory. Okay, and what that theory says is that in any molecule, if there are free or unbound electron pairs, those electron pairs bend the molecule in predictable ways that give molecules predictable shapes. And so based on the number of free electron pairs surrounding the central atom, as well as the number of atoms bound to the central atom, we can use AX notation to predict what shape that particular molecule will be. Okay. If you remember, in order to get a particular molecule's AX notation, you need to first draw the Lewis structure. So what we're going to do together first is practice and review drawing Lewis structures, and then you guys are going to practice and review AX notation so that on Wednesday we can talk about how a molecule's shape affects its ability to either be or not be dissolved. Okay? So let's start here. We have two examples. We have carbon dioxide and water. I'm going to do the carbon dioxide example with you, and then you guys are going to do the water example on your own. Okay, so if we start with our carbon dioxide example, if you remember, the first step in drawing any Lewis structure is to count the total number of valence electrons. Okay, carbon has a total of 4 valence electrons. Oxygen has a total of 6. I have 2 oxygen atoms in my molecule, so I have to multiply 6 by 2, which gives me a total of 16 valence electrons. Okay. Now the next step in drawing our Lewis structure is to subtract the electrons in bonds and the free electron pairs. So the next thing we want to do is come over here and draw our skeletal structure of carbon dioxide. Okay. So if carbon dioxide just had single bonds, the total number of electrons in those bonds would be 4. So now I'll subtract 4 from 16, which gives me 12. Okay. Now, in order to complete the octets on all 3 of these atoms, I would need 6 electrons around this oxygen, 4 electrons around this carbon atom, and 6 electrons around this oxygen atom. Okay. Now, just to review where I'm getting those numbers, each atom needs 8 electrons in its valence shell. These little dashes in between the carbon and oxygen atoms stand for 2 electrons because they stand for 1 covalent bond. So right now around this oxygen there are 2 electrons, so I'm going to need 6 more to finish its octet. Around this carbon atom there are 4 electrons, so I'll need 4 more around that carbon atom, and then again 6 more around this oxygen atom on the other side of the molecule. So if I need 6, 4, and 6, that totals at 16 electrons that I need to get full octets in all 3 of those atoms. So I subtract 16 from 12, which gives me -4. Now, if you guys remember, a result of a -4 when you do your valence electron calculations means that you either have 1 triple bond or 2 double bonds in that particular molecule. Because there are 2 bonds here, that -4 means that we're going to have 2 double bonds in our molecule. All right, so now we've got our 2 double bonds. Now let's finish our Lewis dot diagram because we're not totally done yet. This oxygen atom is going to need 4 more electrons, so it has 2 unbound pairs of electrons. The carbon atom is all set. It has a full octet, 2, 4, 6, 8 electrons around carbon. And then this oxygen atom is going to need 2 pairs of unbound electrons as well to get to that full octet, to get to 8 electrons. So 2, 4, 6, 8. So there's our Lewis structure of carbon dioxide. Now what I want you guys to do is pause the video, and I want you now to draw the Lewis structure for water. Okay, so follow the steps like we just reviewed and draw the Lewis. All right, everybody. So you guys should have just drawn your Lewis structure for water. Now I'm going to show you what that correct answer should have been. Okay. So I'm going to start out by drawing my skeletal structure for water. Next, I count my total valence electrons. Oxygen, using my periodic table, has 6 valence electrons. Each hydrogen atom has 1 valence electron, giving me a total valence of 8. I subtract 4 because there are 4 valence electrons in the bonds in my skeletal structure, which gives me 4. To finish the octets around each atom, I need 4 more valence electrons. Now remember, I don't need any more around the hydrogens because hydrogen only needs 2 valence electrons total, so both of the hydrogens have a full outer shell already. So I just needed to add the 2 pairs here on oxygen so that oxygen ended with 8 valence electrons. So now after you subtracted the 4 valence electrons that you needed to finish oxygen's octet, you get a calculation of 0, which means that you have only single bonds in that water molecule. Okay? All right, so that's our review of Lewis structures. All right. Once you know how to draw a Lewis structure, you can determine a particular molecule's Ax notation. Remember that the A is the central atom. The X stands for how many atoms are bonded to that central atom, and the E is how many unbound electron pairs there are around the central atom. Okay? So for example, in carbon dioxide, our Ax notation there would have been AX2. Because carbon is our central atom, it has 2 oxygen atoms bonded to it, but there aren't any free electron pairs on the carbon itself, so there's no E. Even though there are free electron pairs around the oxygen atoms here, here, and here, okay, and then again here and here, the E is only used if there are free electron pairs on the central atom. And this carbon atom doesn't have any free electron pairs around it, so we don't use an E here. So carbon dioxide has an Ax notation of AX2. AX3 would be an example of a molecule that has 3 attached atoms with no unbound pairs on that central atom. Okay. AX3E, that's an example where you've got three atoms bound to your central atom, but you have 1 pair of unbound electrons also on that central atom. So that's where we use the E for. Okay. AX2E2, that's the Ax notation for water, because you have on your central atom, I apologize, you can't see the hydrogen right there, but on your central atom, which is your oxygen, you have 2 hydrogens attached, so that's where you get the X2, and then you have 2 pairs of unbound electrons also on your central atom, which is where we get the E2, okay, which would give it a bent shape. AX4 is where you have a central atom with 4 atoms attached to it but no unbound electrons. That's a tetrahedral shape. All right, and now we're going to talk about dipoles. So that was a quick and dirty review of Ax notation. You guys are going to have Ax notation charts given to you during class today as you work on this assignment. So that was a quick review of that. Now we're going to review something called a dipole. Okay. Hang tight here and we'll review dipoles in just a second. All right, guys, so let's continue our discussion here. We just did our review on Ax notation. Now we're going to review what a dipole is. And so way back when, you guys should remember doing an activity called polar bears and penguins. That's how you determined if a molecule was polar or not, right? You had to use your electronegativity chart on your formula sheets to determine if there was enough of an electronegativity difference between 2 atoms to see if there was going to be a positive end and a negative end of that molecule. All a dipole is, it's a symbol to show us the polarity of a bond, okay? If you look at this page of your packets, okay, all a dipole is one of these arrows with a positive sign at the very end of it, okay? You use it to show the direction where the electrons are being pulled. So when you draw in a dipole, the end of the dipole that has the point, that's the end of the bond that has a partially negative charge. Okay, so you guys should remember that term, partially negative, and that symbol. We used that symbol on the polar bears and penguins activity as well. So when you draw in this dipole, the end of the bond that has the arrow point should be the end where the more electronegative atom is, because that's the end where the electrons will be concentrated, and that's the end that will have a partially negative charge. Whereas the end where there's the weaker atom, that's the end where you will have a partially positive charge. So that's why you put this little positive end at the end of that dipole arrow. Okay. Just want to be sure we're getting everything here. All right. So in your note packet, it asks you to draw in the dipoles for H2O. Okay. So if we fill in our Lewis diagram from earlier with water. Okay. And if you guys look at your electronegativity charts on your brown formula sheets, if you don't have those out, shuffle around, get those out now. Okay. When you get it out, you'll notice that oxygen is significantly more electronegative than hydrogen is, which means that the oxygen end of our water molecule is slightly negative and each hydrogen is slightly positive. Okay. Now I've drawn in my symbols that show the slightly negative and slightly positive, but as we go forward in our solutions unit, you need to understand this symbol, the dipole symbol. So now we're going to insert that as well. So if we would put our dipoles in for the water molecule, our arrows would you need to have 2 arrows because there's 2 different bonds. Remember that you need to do 1 dipole for every bond when you're drawing in your dipoles, okay? However, in both bonds, the positive end of our dipole is the hydrogen, and the negative end of our dipole goes toward the oxygen. So the point of our arrow needs to be pointed toward the oxygen. The positive end of our arrow needs to be by the hydrogen. So that now we've drawn in our dipoles for H2O. Okay? Now, why are we learning about dipoles now? Why are we reviewing dipoles now? We are reviewing dipoles and polarity because if some of you remember, there were certain molecules that we learned about or practiced calculating polarities for that the bond was polar, but the whole molecule wasn't. Hopefully some of you remember that. The reason for that is because of dipoles, okay? So now in molecules that are perfectly symmetrical, we're down here now, okay? In molecules that are completely symmetrical, the dipoles will cancel, okay? Great example is carbon dioxide. So in carbon dioxide, the bonds between the carbon atom and the oxygen atom is polar. However, because you have one dipole pointing to the left and then a second dipole of equal and symmetrical strength pointing to the right, those dipoles cancel out. So even though the bond itself is polar, the whole molecule ends up being nonpolar because the dipoles cancel. Another great example is carbon tetrachloride. Okay, we've got carbon in the middle, 4 chlorine atoms surrounding it. If you do the math, the bond in between chlorine and carbon is a polar bond. But because you have 4 equal and symmetrical dipoles pulling with equal and opposite strength on that carbon atom, those 4 dipoles end up canceling each other out, so that is a nonpolar molecule. Okay? So that's why we're learning about dipoles now, because as we go into our discussion on solutions, it's very important that you can determine if a molecule is polar or nonpolar, because whether the molecule is polar or nonpolar will determine if it is able to be dissolved or not be dissolved by a particular solvent. Okay, so understanding that in symmetrical molecules the dipoles can cancel is an important thing to know. Okay. All right. So moving on here in our discussion, carbon tetrachloride, even though the bonds between carbon and chlorine are polar covalent, because you have 4 bonds that are symmetrical, those dipoles cancel each other out and you end up with a nonpolar molecule. Okay. Now there are 2 things that I want you guys to write down at the bottom of this page if you've been following along. Okay, so right underneath here there's a little star bullet point there. Okay, I want you guys to write down 2 key ideas from this quick review of molecular shape and ax notation. Okay, key idea number 1 is that any molecule with an ax notation with an E is polar. Okay, so that free electron pair will make the whole molecule a polar molecule. Okay. A second key idea here from our quick review of ax notation and molecular shape is that a molecule that does not have an E and has all of the same type of group on the central atom. Is non-polar. Okay, so 2 main points. Any molecule that has an Ax notation with an E in it is a polar molecule. Second main point, a molecule that does not have an E in the Ax notation and has the same type of group attached to the central atom is a nonpolar molecule. Good example of this second key point would be carbon dioxide or carbon tetrachloride. Okay, great example of this first point would be water. Okay, so what I'm going to have you guys do now, we're going to go through a couple examples of drawing in dipoles. I'll do the first one here with you, and then after I do the first one with you, you guys are going to try drawing in dipoles on your Lewis diagrams, writing out Ax notation, and determining whether or not the molecule is polar. Okay, so let's do the first one together. First one is dihydrogen sulfide. Okay, so total valence electrons here, hydrogen has 1, so we have 2 total valence electrons from our hydrogen atoms. Sulfur has 6, which gives us a total valence count of 8. I'm going to draw in my skeletal structure here. I subtract 4 from my valence count because 4 of my 8 valence electrons are involved in these 2 bonds. Okay. In order to finish my octet, I need to add 2 pairs of unbound electrons to sulfur. So now I subtract 4, end up with a 0 for my valence calculation, which means that I'm going to stay with single bonds in my molecule. My Ax notation would be AX2. X2 is because I have 2 atoms bound to my central atom. E2, because I have 2 pairs of unbound electrons. So because my Ax notation has an E in it, my molecule is polar. Okay? The shape here would be the same shape as water. It would be a bent shape. Okay? So now you guys are going to go through that whole process for all of the other molecules on this page. You're going to draw your Lewis structures. Make sure you're calculating your valence to see if you have any double or triple bonds. After you draw your Lewis structures, you're going to get your Ax notations and the shape. I want you guys to write down the shape as well. And then based on the Ax notation and using our 2 key ideas up here, I want you to tell me whether or not the molecule is polar. Okay? You guys should have plenty of time to finish these. I'd like you to get as far as you can on them. We will touch base on these tomorrow when you get to class. So finish this before you leave class today, and then bring this with you finished tomorrow. All right. Thank you so much, guys. You have a wonderful evening. And I will see you all on Wednesday. Okay? All right, guys. Have a good night. Don't forget to hit that like button and subscribe.